Hello everyone, my name is Pooja Dhengale and I am going to sh- present our research paper which is Design and Optimization of an Ultra Low Voltage Nano-Power LDO Regulator. In my project, I have moved beyond standard design constraint to implement an innovative biasing technique known as subthreshold operation. So I would like to express our sincere gratitude to our mentor Akhil Masurkar sir for his invaluable guidance throughout this journey. So, the problem of the existing LDO is in the modern VLSI, the biggest challenge for system on chip is not just speed, but it's the battery's longevity. So, as we know that most autonomous devices spend 99% of their time in sleep mode. Yet, traditional LDO regulator continue to drain microamperes of current because they are biased in the saturation region, and this creates a power wall. Our goal was to break this wall by designing a regulator that provides a rock solid voltage rail while consuming less than 1 microwatt of total power. So this is the block diagram of our proposed LDO as well the existing LDO. I implement both the LDOs in the cadence. First, I implement the existing LDO. I um, I get the proper that baseline output which already uh, has in the research paper. So to achieve that, we utilizes a strategy called dual axis scaling to achieve the subthreshold operation of LDO. So on the left, you see that the existing LDO, which is a conventional LDO, it runs on 1.8 supply and uses kilo ohm resistor. This is the feedback resistor R of kilo ohm. While stable, it leaks too much current through the feedback network. And on the right, you see that this is my proposed innovation. First, I scaled the supply voltage down to 1.2 volt, and second, the internal bias current is tiny 50 nanoampere, which pushes the transistor into the subthreshold region, which is the region 3. Finally, I innovated the feedback network by using mega ohm resistor. So in my proposed LDO circuit, the resistors value are in mega ohm to effectively choke the static leakage, allowing the circuit to operate at nanoampere scale. So this is the line regulation output of both existing and proposed. So I verify my innovation using a rigorous DC sweep. So in this line regulation plot, I swept the input from 1.0 volt up to 2.5 volt. So you can see that in my proposed design locks on lock होते onto the target point at volt rail, which incredible precision. Okay, so the total line error is only 1.1 millivolt. Hence, this proves that even in the subthreshold region, the error amplifier maintains enough gain to stay immune to battery voltage fluctuation. Next is a load regulation graph in which I analyze this across a nanoampere current range, which is typically for IoT sensor in sleep mode. So traditional design often suffer from overshoot here, but thanks to our high impedance feedback resistor, we kept that voltage deviation to just 1.3 millivolt. So I think this result is the gold standard for nano power design, because it shows that we can achieve a millivolt level accuracy without. To summarize our findings, please look at this comparative table. My baseline design consumed 270 microwatts. My migrating to region 3, which is subthreshold region, and scaling our voltage. So we brought that down to just 1.08 microwatts with a quiescent current of 906.2 nano ampere. So this present a massive 99.6 power reduction. So I successfully demonstrate that the subthreshold biasing is not just a theory, but a viable innovation for the next generation of energy harvesting integrated circuit. For future scope, we aim to integrate an adaptive biasing booster to improve the transient response further. Thank you for your time.